The first step is gathering the data that typically came from different areas of the business itself. Then we need to get a good understanding of the real nature of data, and we can get great support from the graphical representation of variables. The next step is feature engineering, where we can decide to transform some variable before passing them into a machine learning model. After feature engineering, we need to select the features that are most relevant for the model. And for example, in order to prevent overfitting, it is important to exclude the variables with high multicollinearity. Then, we can start with the model building phase, where we typically compare performance of many machine learning models, and we choose the one that gives us the best result. To do that, we typically evaluate many statistical metrics, such as the mean square error for regression and the accuracy or the area under the ROC curve for classification. Last but not least, we also check how the model performance relates to business values. Once we build a model and it brings real value, we can proceed to the deployment on the cloud or in any other business system where it can be assessed in order to get prediction. In practical terms, we need to deploy at least the feature engineering, the feature selection phase, and of course the machine learning model itself. There are a variety of problems that can be found in our variable. Before the definition of the model, it is always important to plot the distribution of our variable, finding unusual observation such as point of leverage, head value, and outliers, and also testing the presence of missing data. And we have to understand if they are missing at random or not at random using techniques such as the shadow matrix. It is quite important also to scale the data. If, for example, we have to measure distances, such as in the k nearest neighborhood, it is necessary to scale the data. We can find, in fact, opposite solution if we merely calculate distances without scaling. For example, we can use the min-max scalar. In another method is the zeta point with mean 0 and standard deviation equal to 1. Most of the algorithms are sensitive to scale, not only the distance space such as KNN, principal component analysis, or support vector machine, but also neural networks and random forest. In some cases, the log transformation can be useful, especially in presence of outliers. The log transformation drives outliers close to the feature average. Feature generation is a process of creating. We can use one autoencoding to reshape the data in order to have 1 when the feature is present and 0 when it's not present. Crucially, when autoencoding is by default already scaled, we can use sparse matrix in order to exclude the 0 and work only when the feature is present. By doing that, we save space in RAM. Note that we can use a sparse matrix only if features with 0 are far less of all the values. It can also happen that a company anonymizes their data, especially in fraud prevention. We can try to find relationship between columns, or if they are grouped in some way, we can check the variance inflection factor to find multicollinearity, finding that anonymized variables have a relationship with some of our features. Moreover, data has to be independent and identically distributed, which is to say, all the data we have collected have no weirdness. Test and training data have the same distribution. That is a fundamental aspect. Data also has to be shuffled. We can plot the values of the feature versus the raw index of the feature and performing the so-called rolling mean in order to smooth the values and better understand the trend. If the data are shuffled properly, we have to expect a sort of oscillation and no pattern are present around the average. At the end, we also have to split the data between the training and test set. The k-fold cross validation method is in this case often used. It can be viewed as a repeated holdout because we split the data into k parts using every part as validation set only once. After this procedure, we average score over those k-fold we created before. The core idea here is to use every sample for validated result. The use of this method is important to check if the data are shuffled, as we said before. After the feature engineering step, we need to perform feature selection. Feature selection refers to algorithms that help to find the best subset of feature from the variable present in our database, called the most predictive feature. Why is feature selection so important? The first reason is that simpler models are easier to interpret by customer. The second reason, a simpler model needs shorter training time and, more importantly, less time to score. We can achieve more generalization with less features, and so preventing overfitting. From the deployment point of view, simpler models are easier to be integrated by the software developers, and so they are easier to put into production. Technically speaking, it means less JSON messages between the software and the model, and less code to handle potential errors. Another important reason to use feature selection is that often we have redundant variables, such as a correlated variable, that provide the same information. This is called multicollinearity. We can check it using variance inflection factor. This analysis tests the ratios of variance to the model with multiple terms divided by the variance of the model with one term alone. There are several ways to take feature selection, and they can be divided mainly in three groups. The first is filter method, such as the analysis of variance or the chi-square test. And these methods are independent of the model that we are going to build. So they are used to provide the first step to remove features, but they don't capture redundancy and the feature interaction, leading us to a poor model performance. Then we have the wrap method. This method considers the feature interaction, but their computation is expensive. They are called, in fact, greedy algorithms because they take into account all possible combinations of the independent variables. The most important wrap method is the stepwise, tested both the archaic index criterion or the Bayesian index criterion. The downside is that this is not a model agnostic, which means that the combination of features that the stepwise found may not be the best for a different algorithm. Then we have embedded method. The classic example of this is the lasso regression, which considers feature interaction and tends to provide a very good model performance. But again, this is not a model agnostics. A model agnostic approach instead is the principal component analysis, which is a data reduction technique that transforms a large number of correlated variables into a much smaller set of uncorrelated variables called principal component. From a deployment perspective, we don't make feature selection part of the pipeline of the deployment process. Machine learning algorithms are a specific topic of statistics called classification. This classifier can learn from data and they improve with experience without human intervention. They are divided into unsupervised and supervised classifiers. Supervised learning uses labeled training data to learn the function that turns input variable into output variable. So it is used to predict the outcome of a given sample when the output variable is in the form of categories. A classification model might look at the input data and try to predict labels such as 6 of healthy or fraud and not fraud. Support vector machine, k-nearest neighborhood, logistic regression for classification are good examples of supervised classifiers. Ensembling is another very interesting type of supervised learning. It means combining the predictions of multiple machine learning models that are individually weak to produce a more accurate prediction on a new sample. Bagging with random forest and boosting with XGBoost are examples of ensemble techniques. Unsupervised learning models are used when we only have the input variable and not corresponding output variable. We have three types of unsupervised learning. Clustering is used to group samples such that objects with the same cluster that are more similar to each other than to the object from another cluster. And a prime example of this is the k-means algorithm. Moreover, association rule is used to discover the probability of the co-occurrence of items in a collection. It is extensively used in market-based analysis. For example, an association model might be used to discover if a customer that purchased bread, for example, in which percentage is likely to also purchase eggs. Another unsupervised learning is the dimensionality reduction, which is used to reduce the number of variables in a dataset while ensuring that important information are still conveyed. In this context, we have feature selection that selects a subset of the original variables. A good example is the stepwise method. We have also feature extraction that performs data transformation from high-dimensional space to low-dimensional space. For example, the principal component analysis is a feature extraction approach. In natural language processing, we also have a very useful unsupervised algorithm called topic modeling that is used to find the topic discussed inside a text. For example, we could be interested to understand what are the main topics discussed on social media. Once we have the data and we pre-process the data, engineering the variable, and we already selected the most important features we want to use, it is time to build the machine learning model, such as supervised or unsupervised model. A crucial stage is to evaluate the performance of the model we have identified. And in classification, we have soft label, scroll probability, and hard label, the label of the classes based on the automatic threshold that we found thanks to the confusion matrix. We can test the accuracy, which is the number of observations predicted correctly divided by the total number of the test sample. But what is wrong with this? It can lead us to a wrong conclusion in case of very unbalanced data, which is common to have in fraud prevention. In order to overcome this disadvantage, we can use precision or recall. Moreover, to prevent this class imbalance problem, we can use a technique called synthetic minority oversampling technique, or SMOOTH for short. The raw curve and the area under the curve method is also used for each probability value to test how many times the model made a good assessment, but also how many times the model made a wrong assessment. It evaluates, in fact, the ratio between the false positive and the true positive. We should not forget that false positive improperly reporting the presence of a condition when it is not in reality. On the contrary, false negative improperly reporting the absence of a condition when in reality it is not the case. For example, not detecting a disease when the patient has this disease. All these values are summarized in the confusion matrix. Based on confusion matrix, we can decide our threshold to obtain a hard label from soft labels. A crucial aspect to take into consideration is that many times we build multiple machine learning models, and then we have a meta model that takes into consideration the prediction of all the initial models and combines them to make a better assessment. This procedure is called meta-ensembling. A fundamental aspect to learn is how to take the machine learning model from the research stage to a fully integrated API that can be coached live and utilize live data to make predictions. No machine learning models brings true values until it is fully integrated and can be used to score real data. At the same time, this is the most difficult and challenging part of any typical machine learning pipeline. Model deployment is the process of integrating a machine learning model into an existing production environment. It needs the coordination between data scientists, IT teams, and the DevOps software developers. In fact, there is often a discrepancy between the programming language in which the machine learning model is written and the languages used by the production system. This can delay the project timeline by weeks or even months. We have to consider that model deployment means not just to deploy the algorithm, but the entire pipeline that will allow us to get the data, transform the data, and select the most relevant variable that will be used in our model. Deploying a machine learning system is relatively fast, but maintaining the system effectively over time is difficult and expensive. The machine learning system requires close collaboration between data scientists, data engineers, and DevOps, as well as the business expert. This requires a shared understanding of the system architecture and a responsibility for an effective cooperation. There are many challenges in the machine learning system. First, we need reproducibility and entanglement. In fact, over time, the quality of data might change. There is also the challenge to be flexible, to configure the basic fact of the model, such as preparing the data in a friendly machine learning format. We have also to take into account the extensibility, which is the ability to easily add and update the model, and also scalability, which is the ability to serve a model prediction to a large number of customers. The most important aspect is that all the steps in the pipeline have to be reproducible. This means to have identical results given the same data, both in the research environment and in our production environment. For example, we cannot reproduce a training set in the production environment, because some databases are constantly updated and this override our previous record. So the data that we're using today could not be the same data in a week from now. Another problem is that SQL loads data randomly, resulting in a reproducibility problem. And this is due to the fact that when we split the data in training and test set, we use a random function. So, in order to minimize the impact and ensuring reproducibility, we can save the snapshot of the training data in a storage such as the AWS S3. It is also important to record the order in which we pass the features in the model, such as record the hyperparameters that we are using. And for model that requires an element of randomness, such as random forest or neural network, we have to remember to set the seed. R in Python is a data science love story. Many data science teams today are bilingual, leveraging both R and Python in their work. But while both languages are tremendously powerful, teams frequently struggle to use them together. But it is possible to combine R and Python code in a single data science project, leveraging a single infrastructure such as the Jupyter Notebook as well as the RStudio IDE. In a classical situation, on one hand, we have multilingual teams struggles to collaborate and they are forced to do repetitive analysis. On the other hand, business leaders struggle with the low iteration time and they are worried about the value of their data science investment. And the risk is that they fall back on intuition that leads to suboptimal decision. The use of RStudio allows us to address these problems because it allows us to combine R and Python code together in a single project using the reticulate package along with the Markdown. Often, the data science team are responsible for the deployment of machine learning model. And we can host our model that we made combining R and Python code in a single RESTful API. From the DevOps and IT perspective, we can provide a single infrastructure to configure, integrate scaling, securing just one, as opposed of multiple times. From the perspective of a data science leader, we can deliver regularly updated results, customer report, self-serve app using the Shiny in a single location. This can give the right answer and insight to the business stakeholder in order to make better decisions. There are many advantages of using cloud services over other types of hosting. The key aspects are, first, high availability. In what percentage of the time our system responds to users' requests properly. In cloud computing, we can reach a very high percentage of uptime. Second, scalability, which is the ability to handle growth of users. And again, we can reach a very high value of failure point without having the support of the cloud. Elasticity, which is the ability for a system to automatically grow or shrinkage based on application demand. Agility, how quickly the system responds based on changes in the environment. Fault tolerance, how a system handles failures such as power down, network failure, and hardware failure, and how much the data is recovered after a data loss. In fact, we have the possibility to have an automated backup and recovery and mitigate the risk of losing our data if there is any unforeseen failure or interruption. For example, in HDFS, we use blocks that are replicated 3 times to support fault tolerance. Starting from 2013, there is a flexible alternative to MapReduce, which is Spark. The advantage is that it can use data stored in a variety of formats such as AWS S3 data storage. With the release of Spark 2.0, Spark is moving toward a data frame-based syntax, and so when we're working with pandas or a spreadsheet, those are more like columns and rows, but with the advantage that these are data sets and these are still resilient distributed. Resilience means the ability to be recomputed and it is distributed to different nodes across the cluster to achieve parallelization. There are also tools such as Microsoft Azure Databricks or AWS Elastic's MapReduce platform that allow us to use large clusters with a very quick setup. In Microsoft Azure, a very interesting topic is the integration of RStudio with Azure Databricks and Spark, where we can write our code using online version of RStudio by taking advantage of Spark cluster. This approach is extremely useful for parameter tuning. For example, imagine that we have to choose the right value for the k nearest neighborhood. The aim is to have the error rate of all the permutations of the parameters in order to check which combination performs better. And of course, we can also find which are the columns, our independent variable, that cover the response variable. It is an area of machine learning and AI concerning with the interaction between computers and human natural language. In particular, how to program computers to process and analyze large amounts of natural language data. Computers are very good to handle numerical information. On the contrary, text data is highly unstructured. Natural language processing attempts to use techniques in order to create structured data from text data. For example, we have tokenization, which is the process of breaking up the original text into component pieces of the original text. Then we have another process which is called stemming. Stemming is a process to exclude the variation of a word and cataloging related words. It essentially chops off letters from the end until the stem is reached. Unfortunately, English has many exceptions where a more sophisticated process is required, called lemmatization. In contrast to stemming, lemmatization considers the entire vocabulary in order to apply a morphological analysis of the word. For example, the lemma of was is bee and the lemma of mice is mouse. Feature extraction is a process to extract from text the raw text from numerical features. For example, we could count the occurrence of each word to map text to a number, called count vectorization. For a large corpus, in order to reduce the sparse matrix, which is a matrix with lot of zero, we can use the document term matrix. Or, as an alternative, the TF-IDF vectorizer is used. It allows us to understand the context of the word across the entire corpus of the document in terms of just its relevant importance in a single document. It is a process to find text similarity using vector space models such as word2vec. Having enough data, we can make highly accurate guesses about the word meaning based on past appearance. We can evaluate the neighborhood of a word using the cosine similarity. What is interesting here is that we can perform a sort of arithmetic with the word vector. We can also predict the target word using a method called continuous bag of words. And continuous bag of words is an extension of the big grammar, where we try to predict middle word from the surrounding word. Typically 5 or 10 words are used, and of course this is a hyperparameter that may require some tuning. Or we can use a word to predict a target context, which is called skipgram, that uses the autoencoder neural network projection. Having the middle word, we can try to predict the surrounding word. From my experience, I also had good results adopting social network analysis. Here the nodes are of course not people but words, and their relationships are represented by the edges between nodes. I use it successfully for the analysis of the presidential election in Romania. This is a version of unsupervised learning that allows us to clustering documents into topics. So we have unlabeled data, and our goal is to discover the topic underlying the documents. The key aspect to keep in mind is that we don't have the right topic to begin with. All that we know is that the documents that cluster together share similar idea, but it is up to the user to identify what this topic represents. The most popular topic algorithms are latent direct length allocation, LDA for short, and LDA to VEC, which is an hybrid algorithm combining the best idea from LDA and work to VEC. The assumption of latent direct allocation is that documents with similar topic use a similar group of words, and we can find this group of words that occur together across the corpus. Having the probability distribution over words, we can identify the topic, and because it is an unsupervised technique, LDA is not able to tell us the topic directly, but it is up to the user to interpret those probability distribution as topic. From my experience, to get the best interpretation, we need the help of a domain expert. For example, if we are analyzing text from social media, the contribution of a social media specialist might be helpful. A critical point before starting the LDA is to have a sort of intuition over how many topics we have. This is fundamental to reach a steady state where the assignment of a word to a topic are acceptable. The word and topic don't change so often and become pretty steady. We mentioned before LDA to VEC, which is an hybrid algorithm combining best idea from LDA and work to VEC. The power of LDA to VEC lies to the fact that word to VECs help to predict word inside a sentence, and so it is a local predictor, while LDA captures long-range themes instead of focusing over thousands of words, and so it is a global predictor. Crucially, LDA to VEC predicts globally and locally at the same time. Examples of sequence data are time series or sequences such as natural language processing. Recurrent neural network is specifically designed to work with sequence data. In a normal neuron, in feed-forward network, the inputs are aggregated and passed through an activation function to obtain an output. On the contrary, a recurrent neuron sends output back to itself. We repeated this process many times, and we call this process unrolling the recurrent neuron. The neuron receives both input from the previous timestamps as well input from the current timestamp. This type of neuron with two inputs are called memory cell because it retains the memory of the past timestamp. For example, an example of this is the sentiment analysis. We can feed in a sequence of words the tweets of a movie review, for example, to calculate if the sentiment is positive or negative. On the opposite side, we can also feed a single input at the timestamp 0, having as an output a sequence network. The single seed word could be, for example, the word hello, that is able to get out an entire high probability sequence of phrases in output. This is an example of vector-to-sequence network. Most of the time, we want to have a network aware of not just the most recent text, but also the entire history of texts. In this case, the long short-term memory unit is used. In fact, if we are dealing with a very large sequence, the recurrent neural network tends to forget the first input. We need a balance for both the short memory, such as the recent training data, versus the long-term memory, such as the first data that we begin train on. The first step of the long short-term memory unit process is the so-called forget gate layer. Here we decide what information to forget and not to be taken into consideration from the neuron state. The calculation is made by the sigmoid function, where 1 is what we take and 0 what to forget. That is why the sigmoid function is also called input gate layer. The next step is to decide what is the information to store in the network state. We use the hyperbolic tangent function, which creates a vector of the so-called new candidate value. A variation of the long short-term memory unit is the gated recurrent unit, which is simpler than the LSTM model, and because of that, it is increasingly popular. In machine learning, we optimize lots of stuff. For example, in linear regression, we optimize the intercept and slope, or in Disney, we optimize clusters. The interesting thing is that gradient descent can optimize all these things. A good example is the sum of the square residuals in regression. In machine learning lingo, this is a type of loss function. And of course, the residual is the difference between the observed values and the predicted values. Gradient descent identifies the optimal value by taking big steps when we are far away to the optimal sum of the square residual and start to make many steps when it is close to the best solution. Then we can calculate the derivative of each point of the function. In other words, we are taking the derivative of the loss function. Gradient descent uses derivative in order to find where the sum of the square residual is lowest. The closer we get to the ultimate value of the intercept, the closer the slope of the curve gets to 0. Gradient descent stops when the step size is very close to 0, and the step size is close to 0 when the derivative is close to 0. When we have two or more derivatives of the same function, in this case the derivative of both intercept and slope, we call this a gradient. We use this gradient to descend to the lowest point in the loss function, which in this case is the sum of the square residual. One last thing is that when we have millions of data points, the process may take a long time. There is a thing, stochastic gradient descent, that uses randomly select subset of data at every step rather than the entire data. This reduces the time spent calculating the derivatives of the loss function. Deep learning neural networks are trained using stochastic gradient descent algorithm. And stochastic gradient descent algorithm is an optimized algorithm that estimates the error of the current state of the model using samples from the training dataset and then update the weights of the model using the back propagation of errors. The amount that the weights are updated during training is referred to the step size of the learning rate. During training, the backpropagation estimates the amount of error a node in the network is responsible for. Crucially, instead of updating the weights with the full amount, it is scaled by the learning rate. So the learning rate hyperparameter controls the rate or the speed at which the model learns. Generally, a large learning rate allows the model to learn faster, but at the cost of arriving at a suboptimal final set of weights. On the contrary, a smaller learning rate may allow the model to learn a more optimal or even globally optimal set of weights, but it may take significantly longer to train. In order to accelerate the learning rate, we can use gradient descent with momentum. Momentum is an advanced optimization algorithm that speeds up the optimization of the cost function. It makes use of the moving average to update the trainable parameter of the neural network. There is also a problem called local optima. It is quite common, in fact, to get stuck to the local minimum rather to find the way to the global optimum. The problem is that most points of zero gradient are in the so-called saddle point. Saddle point has derivative equal to zero, and we have the problem of plateau, which is a region when the derivative is close to zero for a long time. The consequence is that the process takes a long time before realizing to follow the correct path in order to reach the minimum. This is the scenario in which more sophisticated algorithms such as adaptive momentum can speed up the learning rate. So we have many hyperparameters in artificial intelligence, such as alpha learning rate, the momentum beta, beta 1, beta 2 and epsilon in adaptive momentum, the number of layers, the number of hidden units, the learning rate decay parameter, and also we have to check the size of the mini batch. And in fact, for those reasons, it's a common practice to sample the parameter at random using grid search and systematically evaluate the values.